Okay, let's go ahead and get started here. So I'm Jeff Wittich. I'm the Chief Product Officer at Ampere Computing, and I want to talk to you today about how to build sustainable computing in the age of AI. So I'll take you back a little bit. If you're not familiar with Ampere, we are about a 6-year-old company, and we were founded to become a modern semiconductor company with the goal to create the first cloud-native processors for the sustainable cloud. If you go back about 5 years, we foresaw some of the current challenges that exist within the data center space. You've seen these stats a million times now. The data center space is responsible for somewhere around 3% of global power consumption, and thereby also around 3% of global CO2 emissions. And AI is only accelerating this trend. And so when you look back at the founding of Ampere, again, we foresaw that this was going to be the major limiter to compute growth going forward into the future. We have a global imperative to increase data center efficiency so that we can continue to build out more and more compute with AI as the big driver. Not only is it the responsible thing to reduce the overall power consumption, but it's also a mandate in specific geographies. You've seen all of the stories about power constraints in places like Amsterdam, in London, in Santa Clara County here. You can't build new data centers. There's no available power on the grid today. So this is the largest constraint, the largest challenge we have today to the data center space. On top of that, power costs continue to increase. So whether your concern is sustainability, cost, or just availability of compute, we need to do things differently. On top of that, nothing new here. We've been in this cloud era for the last decade plus, which looks very different from the eras of the past. And we've seen these types of shifts in the compute paradigm previously. We saw the shift from mainframe computers to the client-server model, and then we saw the shift to cloud roughly 10 or 15 years ago. But while the entire infrastructure model has changed, and while the software model has changed, what hasn't really changed is the underlying hardware. This is why we've developed a new type of CPU. We call it the cloud-native processor, but it's a general-purpose CPU that's exceptionally well-suited for cloud environments, for cloud workloads, and is specifically designed to deliver amazing compute scalability at very, very high efficiency. If you look at the technology space then around CPUs, one trend is that the techniques that were used over the last 4 or 5 decades just don't scale anymore. It's no longer possible to continue to increase the frequency of processors. That ran out in the early 2000s. We see the end of Dennard scaling, so there's no longer a free lunch. You don't get increasing transistor count in the same area at the exact same power. You end up seeing power density increases over time. So what this means is we need a completely different way of thinking about CPU development and building CPUs. The traditional techniques don't work any longer, running at extraordinarily high frequencies. Things like hyper-threading doesn't provide the type of scalability that cloud providers and cloud users want. And a lot of accelerators, while they may provide high performance for very specific tasks, it's not a general-purpose solution. So at Ampere, we focused on delivering very, very power-optimized, consistent performance, linear core scaling, and very high-performance general-purpose cores. And I'll show you a little bit about why that's so incredibly important. The net result, though, is that we have changed the paradigm when it comes to performance and efficiency. Instead of continually moving up to the top right of this chart, using power to deliver more and more performance, we're moving down to the bottom right. That is, we're increasing performance while decreasing the amount of power consumption. And given that power is the main constraint at the rack level, at the data center level, globally, efficiency leads to higher performance at scale. We've developed a number of products that are in market today, starting with the Ampere Ultra and Ultra Max processors that we released over the last couple of years. 128 core products, widely adopted across many, many clouds around the world, as well as being adopted by enterprise users who are buying servers from ODMs and OEMs. In May, we announced our new product, AmpereOne. That's a 192 core product. that's delivering amazing levels of performance and efficiency. I'll show you a little bit more about the performance it delivers going forward. And all of this required a fundamentally new approach. With AmpereOne, that's our first product that uses our own custom cores, which again have a very unique microarchitecture that solves both the efficiency and the performance problem. When you look across the overall environment, we're tackling problems everywhere from the edge, where something like our 32-core 40-watt part is an exceptionally good fit. As the edge looks more and more like the cloud, as high-performance workloads are run at the edge, this becomes critically important. The amount of power available isn't increasing, but the compute demands are increasing rapidly at the edge. And then all the way into core data centers that are using our 128-core Ampere Ultra processor. And then if you've seen some of the announcements over the last month and a half or 2 months, also using our AmpereOne processor in places like Google Cloud and in Oracle Cloud. So we have a wide variety of solutions that span everything from 40 watts up into the 300-watt range. So ideal solutions for a broad range of environments. So specifically looking at AmpereOne. With AmpereOne, the goal was to deliver more of everything. It was to deliver more compute via more cores, 192 of them, deliver more memory bandwidth with DDR5, deliver more I/O bandwidth and capacity with PCIe Gen 5. It delivers the highest overall performance, scalability, density for cloud workloads, and it really extends the feature set that we introduced starting in the Ampere Ultra family. So let's go in a little bit about what it is that makes our processor so unique. I mentioned it really comes down to a fundamentally new approach to how we architect and design a CPU, looking specifically at the needs of the cloud. What does the cloud require? The cloud requires high performance that's predictable. It requires elasticity and scalability, and it requires efficiency for high density. We delivered this in a number of ways. We delivered a foundational microarchitecture that's more efficient and higher performance. We enabled unique features, and then we delivered leadership performance in cloud workloads. So let me talk about some of the things that are particularly unique. We've adopted a different approach than x86 when it comes to designing our cores. Our cores are all single-threaded. The reason is this. When you look at the way that scaling might occur in the cloud today, let's say something like an inference workload. So you start out with a single vCPU, which is a single thread. And in the case of something like Genoa, you add a second thread, which is actually just another thread within the exact same physical CPU. You get about 6% more performance from adding that second thread. And the reason is because you're still sharing the L1 and the L2 caches. It's the same execution engine. You're just oversubscribing the resources that you have. So if you have a really inefficient core, it's a way to suck up some of the resources that aren't always being used. It also creates a lot of contention. You have resource contention. You have contention between various users. And you don't get that much incremental performance. Instead, with our approach is add a new thread. It's a new core. Has all of its own resources. Our cores are really efficient, so we don't need to go and oversubscribe them in order to suck up extra cycles. So the extra thread that you've added, which is an extra core, you get 2x the amount of inference performance, kind of what you were expecting. So you have great scalability. Net of it is SMT or hyperthreading, not well suited for the cloud. Single-threaded cores offer more predictability, and by offering more cores, that's more work. Another thing is the way that you actually architect the product itself. The topology of the product really matters. Now, it's an easy thing to do to take kind of existing building blocks that you might have, reconfigure them into a higher core count product. The problem is that you have multiple chiplet boundaries across cores where the processing is actually occurring. That leads to a lot of jitter in latency. Latency is incredibly important in the cloud. This is performance of Redis, so caching software. This is the 99th percentile latency across a number of runs. You can see here, AmpereOne, because it has a monolithic compute die with a single mesh that's connecting all of the cores, we have very, very low and predictable latency across runs. In the case of EPYC, you're traversing the chiplet boundaries constantly. That results in a lot of added latency, and even worse, huge unpredictability. These are very, very large latency tails, 10x what we see on AmpereOne. So the product needs to be very scalable across the cores. And then lastly, it needs to be incredibly efficient. Now, one way to deliver efficiency is to deliver cores that don't consume very much power, which we've done. But the other piece of efficiency is how highly utilized is the system. With our approach to having a very, very highly scalable processor, one that doesn't have a bunch of bottlenecks, ones that isn't where you're not contending for resources, we're able to deliver linear scaling all the way up to 100% utilization. So why does that really matter? If you look at the x86 processor here at Genoa, you start to see a big roll-off around 50%. So by the time you get to about 60% utilization, you only have 10% performance headroom left. So if you want to leave a little bit of extra headroom for some bursty workload that comes in, you're probably not going to load the CPU up past 60%. You might even be running it a lot lower than that. In the case of AmpereOne, well, you can load it all the way up to 90%. You still have 10% headroom left. So this is a much, much more efficient way to deploy workloads in the cloud. Run at very, very high utilization, and then that multiplies the efficiency that was inherent in the CPU cores themselves. So very different approach. What's the net result? Let's look at some cloud workloads. So this is AmpereOne, our 192 core processor. This is against AMD Genoa and against AMD Bergamo. And you can see here, up to 50% higher performance at the rack level than Genoa, up to 68% higher performance at the rack level than Bergamo on something like Redis. Large leads across the board. Redis, Nginx, H.264, very, very high performance. And how did we get there? So let's just dig into something like Redis. So it does start with delivering more performance at the CPU level. This is because of the performance of the cores, the efficiency, and also the architectural features that I mentioned earlier. So we deliver higher performance per core. That's being done at much lower power. The power being consumed here is about 240 watts for the AmpereOne 192 core part. It's over 300 watts for both of the AMD parts. So we're doing this at lower power. And then when you couple the efficiency with the higher core count, you get amazing density at the rack level. The other thing is that when it comes to the AMD systems, they have 50% more memory channels. The problem with that is that means that's a considerable amount of additional cost at the server level to populate all the memory channels to get balanced performance. And that's also a large power adder as well. So we can deliver much higher performance at the rack level, which is what really matters. If you can deliver more performance at the rack level, that's more capacity at the rack, that's more capacity at the overall data center level, given that everyone's constrained by either power or by space, which are the constraints here in this example. So leadership performance with AmpereOne, well surpassing what AMD has been capable of doing, and doing so in a way, as you saw with some of the earlier examples, in a way that delivers some unique performance attributes that the cloud really values. It's also about features. So there's a couple of features that we've developed that are also unique to our Ampere CPUs. Back in May, when we launched AmpereOne, I talked about 9 different features across 3 categories. I'm just going to talk about 3 today, just to give you a taste of what we've done. The first feature that I wanted to talk about is memory tagging. Memory tagging, it's a very powerful tool for detecting and preventing bad pointer references to memory. Why does that actually matter? It matters for 2 reasons. One, security. One common attack in the cloud and enterprises is a buffer overflow attack. So you're trying to overflow the buffer and then get into memory spaces that you shouldn't have access to. What we're doing with memory tagging is we do one last check to see if the tag in the address space actually matches the tag that was provided in the user space. And so if you tried to execute a buffer overflow attack, you get stopped at the end because they don't match. The other thing is it protects against coding issues. There's times when metadata is corrupted. You want to know that. This allows you to detect things like that might occur, say, in really large databases. This is something that cloud developers, users, providers, they've been asking for over a decade for these types of multi-user environments, for large databases. We introduced this in our cloud-native processors. It doesn't exist in x86 CPUs. And actually, specifically, we had one of these customers talking about this in June. Oracle, for instance, is a user that sees great value in memory tagging. Another thing, we have memory and SLC QoS enforcement. What we've done here is we developed a very, very precise and granular mechanism for monitoring and controlling the usage of shared system resources. I showed you earlier that we try and keep as many resources unshared as possible. With single-threaded cores, we don't have to share the L1, the L2 cache, the execution engine, but you do still share the SLC, which is the system-level cache, and you do still share the DRAM. So that could create contention, that can create bottlenecks between users. You want to mitigate that. So it guarantees that any of those shared microarchitectural resources are allocated to the higher priority tasks, and then it also controls any adverse performance effects if you have misbehaving software. If someone's actually going in and maliciously trying to hog all the resources, you can create fairness algorithms to ensure that doesn't happen. This is incredibly important in multi-tenant environments so that they can deliver consistent performance to multiple users and to meet their SLAs. And we did this in a very unique way that is incredibly granular and precise. And lastly, we have a feature that we call mesh congestion management. So this is a very sophisticated feature that manages the traffic. We have that big monolithic mesh spanning all 192 cores. As I showed you before, that's ideal because that keeps all of the traffic on one single compute chiplet. What we need to then do is to intelligently manage the traffic around that mesh so they don't create bottlenecks. So for instance, this reduces the latency of the traffic from cores to other cores, or SLC, or to memory, or to I/O. Another thing is that there might be times where the mesh is congested, and you know that if you evict the contents of the L2 cache, you know that you're not going to get new data anytime soon. And you might actually want to reuse the data that you were going to evict before you ever even get the new data coming out of memory. So in this case, we prevent needless requests from the L2 cache so that we minimize those delays. So we adjust the request rates from the L2 cache in response to real life and real-time traffic. Any kind of a high-performance scalable cloud environment has to deliver consistent performance, and this, in addition to the large mesh, enables us to do this and eliminate bottlenecks. And you can see there, with mesh congestion management, and without mesh congestion management, we have about a 3x delta in memory latency. So this does a huge job in providing that nice, consistent memory latency, even when you have aggressor threads that are trying to throttle other cores. Okay, so I did start at the beginning and say this was also about sustainability, scalability in the age of AI. So I'd be remiss if I didn't also talk about how our processors perform when it comes to AI. From an AI inferencing perspective, we're enabling people to build GPU-free inferencing servers. You can see here, compared to all the common CPUs that are available out in the cloud today, I picked just the ones that are readily available today. So this is our 128-core Ampere Ultra Max versus Genoa, Ice Lake, Milan. If we compared AmpereOne to these processors, obviously the lead would increase even further. You can see there the inferences per second, kind of as input on the left side. But what's really important is what's the performance in terms of inferences per second that you can get per dollar, per watt, and per rack. And you can see there we have a large lead in things like recommendation engines and in computer vision with ResNet across the board, whether it's performance per dollar in terms of system cost, performance per watt, performance per rack. So all the things that really limit you in the AI space, we provide a superior solution. And given the fact that GPUs are very, very expensive, consume a lot of power, and are also hard to obtain these days, I also wanted to show you how, say, a Gen AI model like Whisper does. So Whisper is providing speech to text, so doing, say, voice translation. Let's say real time, you're trying to provide closed captioning in, say, 100 languages real time. You might use Whisper. So now we've thrown in the A10 and the T4 where people might be tempted to use a GPU. And you can see here that the results don't really change. For one, GPUs don't do a particularly good job at a lot of these types of workloads for inferencing because there's a lot of latency incurred from moving back and forth between PCIe. Also, they're not really fully utilized. They may do a great job at training. Inferencing isn't as dense of a task. So you can see here, throw in the GPUs, results the same. Ampere still delivers the best performance per dollar, the best performance per watt as well. And then I thought I'd also show, well, what happens in the cloud? Because not everybody here is maybe buying or building their own servers. You might actually be using instances that are out there in the cloud. So here are a bunch of AWS instances with GPUs, with Graviton, with Intel, with AMD, all the stuff that's out there right now that's the latest gen available in AWS. And you can see here, now it's inferences per second per instance cost, because that's all you're seeing is the instance cost. And you can see here across all of those same types of models, your best choice is to run a cloud instance that's based on Ampere. Okay, so that's one of the things that we're doing from an AI perspective. All those benefits that I showed earlier with all kinds of cloud workloads, they all apply for inferencing as well. So we can help to solve the scalability, the efficiency, and the cost problem in the AI space just by helping people run on really versatile CPUs that are incredibly efficient. And the bonus is you can run any workload on these as well. We have a number of customers that are doing this today, people like Lightly, Wallaroo, Matoha, Alodal, running across GCP, Azure, Oracle, and they're seeing these types of big advantages. They're seeing more performance, lower cost, better performance attributes as well, better consistency of latency. But that's not all. While obviously our CPUs are a great solution, I also want to announce a new industry group that Ampere has kicked off. We announced this last night at an event that we hosted. It's called the AI Platform Alliance. Obviously, there are many, many solutions to solving AI problems, not just running on the CPU, and obviously not just running in GPUs either. So our mission here with creating the AI Platform Alliance was to make AI platforms more open, efficient, and sustainable to everyone, making it possible to deliver sustainable AI at scale. Because obviously, we're moving to a future where AI is going to be broadly utilized around the world by everybody, and we need to do this in such a way that doesn't negatively impact the environment. So we're helping to develop an ecosystem around AI hardware solutions and complete solutions that deliver better efficiency, better sustainability, and importantly, to do so in an open ecosystem without lock-in from a hardware or a software perspective. And so we've launched this and want to announce the first members of our alliance. We have 10 members of the alliance. We'll be adding more members here very shortly. We have members like Cerebras, Furioso, GraphCore, Calray, Canara, Luminous, NewChips, Rebellion, Sapion, all people who are developing really, really innovative solutions for AI training, for AI inferencing, really challenging the status quo. And so our goal with the alliance is to build an ecosystem of innovative hardware providers to provide lots and lots of choice for the industry, to build platforms that are easy to deploy around them, and as we gain traction with this, to build entire solutions spanning the software stack as well, so that people have choice, so that people aren't locked into the same exact GPU and x86 CPU solutions that they've had to work with for the last couple of years. So really excited about the AI Platform Alliance. You can go check out the site. It's platformalliance.ai. If you are building a hardware solution for AI, you can apply to join, and we'll continue to add members, and you'll continue to see more and more from the Alliance as we develop joint solutions, benchmark them, and develop solutions that can be easily deployed across the entire ecosystem. So I think a really, really valuable thing for the ecosystem, so it's not just about Ampere building processors that are incredibly efficient, it's about developing an entire ecosystem. So lots of great stuff here at the rest of the Global Summit. So if you're walking around the floor here, a lot of places to see our platforms. You can check out demos, some of our partners, AmpereOne platforms running live demos in our Ampere booth. But we also have our platforms and products in a bunch of other booths as well. AMI is showing off their scalable heterogeneous firmware management system. That's helping people to be able to more seamlessly manage an environment where you have many, many platforms from many, many vendors, and you have many different firmware releases. So check that out. ARM has different platforms in their booth, including one with a number of GPUs in it, so kind of great thing for AI, as well as an edge platform. We've got ASRock Rack that has a micro ATX Ampere Ultra platform. Gigabyte and Hive both have AmpereOne platforms in their booth. HP, you go check out the ProLiant RL300. That's a great choice for enterprises and cloud providers looking for kind of a rock-solid platform that looks exactly like every other ProLiant platform with the same ILO or OpenBMC support. We've got Supermicro that has an edge platform, AmpereOne platform, and lastly, Pegatron has both Ampere Ultra and AmpereOne platforms. So a lot of platforms around here to go check out. And like I said, check out our booth, ask us tons of questions, and hopefully you are able to leverage either Ampere technology, Ampere CPUs, build a better sustainable solution, or want to partner with us to build hardware solutions, software platforms. So come up, check it out, and thanks for attending today.